In this tutorial, we'll practice linear interpolation of data, specifically data from the lookup tables in the back of your thermodynamics book. For this tutorial, you'll want to have your book handy. I'll refer to specific tables in the appendix, and you should make sure that you can find the data along with me. That'll make it a lot easier when you have to do this on your own. So the question we're trying to answer is, what is the specific volume of a refrigerant, R134A, at a pressure of 2.4 bar and a temperature of 23 degrees Celsius? A lot of problems in your book work this way. They'll either ask you for some particular property given some other properties, or you may even, as part of a larger problem, need to know some substance's particular state. The way to figure this out is to go through and find all of this data in one of the lookup tables. So let's focus on the pressure here, 2.4 bar. You could also look it up according to the temperature, but I'll pick the pressure. And the first thing I would do is to have some expectation for what should happen in PVT space. Let's pick a TV plot. And you may remember that an isobar that passes through the vapor dome looks something like this. Characteristically, it has a shape something like that, where it starts in the lower left, goes horizontally through the vapor dome, and then curves up and to the right in the superheated vapor state. So we can imagine that this could be an isobar for 2.4 bar. Now we'll actually need to confirm that. We don't know in advance. 2.4 bar for this substance could actually be well above the vapor dome or something, but a reasonable first guess is that there will be some part of this isobar that passes horizontally through the vapor dome. So now we can look up this substance, and it's R134A, so we'll look in the index to tables and SI units near the back of our book. I'll give you a moment to do that, either with your physical book or an ebook. And that will help you to find this particular substance. You don't accidentally want to look up water or something when you're looking for this refrigerant. So sure enough, we look through the index and we see that R134A has a temperature table, a pressure table, and a superheated vapor table. So there are three options. Well, we decided to emphasize the pressure, 2.4 bar, so let's look at the pressure table first, which is table A11. So we look up 2.4 bar on this table, and the leftmost column features pressures. Sure enough, there's a pressure of 2.4 bar. And I look at it, and immediately next to it see a temperature that corresponds to the temperature in the vapor dome. Because remember, table A11 will be for a saturated refrigerant, 134A, so it's in the liquid to vapor transition. That means inside the vapor dome. Well, according to the table, inside the vapor dome for this substance, at 2.4 bar, the temperature is minus 5.37 degrees Celsius. So I'll put in a horizontal dashed line corresponding to that temperature on our TV plot. But remember, the temperature that we're interested in determining the state for is 23 degrees Celsius, so substantially higher. What does that mean? Well, that temperature would be somewhere up here on our TV plot, and to intersect 2.4 bar, that would have to happen to the right of the vapor dome, so we have to be dealing with a superheated vapor. Alright, we looked in the wrong table, but at least now we've confirmed the state, indeed it's a superheated vapor. Fortunately, the book has a table for R134A in a superheated vapor state, and in fact it is the next table, table A12. So we scroll down or flip to table A12, and now we see that for a superheated vapor there are these sets of tables arranged according to pressure. So the very first one is 0.6 bar and it goes up from there. If we search through these various tables, we eventually find a pressure of 2.4 bar, which is what we want. There's a problem though. We're looking for a temperature of 23 degrees Celsius, and we don't have 23 degrees Celsius listed on that table. If you can see, on the far left side where the temperatures are listed, we're given the temperatures 10, 20, 30, 40 degrees Celsius, etc. So we have 20 and we have 30, but we don't have 23 specifically. This is where linear interpolation comes in. So what I'm going to do instead is to look up the two nearest neighbors in terms of temperature to the temperature that we're interested in. For this table, again, under the 2.4 bar pressure entry, we would look at the entries for 20 degrees Celsius and 30 degrees Celsius, since those are the two temperatures nearest to 23 degrees Celsius on either side. So we look at that, and we can get the specific volume in each of those two temperatures. So for this pressure and 20 degrees Celsius, the specific volume, which I'll subscript 20 just so we remember it corresponded to 20 Celsius, is 0.09399 cubic meters per kilogram. We look up the entry for 30 degrees Celsius. V30 is 0.09794 cubic meters per kilogram. Our goal now is to use these two data points to construct an accurate estimate for the specific volume at 23 degrees Celsius. To do that, let's zoom in on this little region right around our point at 2.4 bar and 23 degrees Celsius. So if we zoom in on this, the idea is that we have data at 20 degrees Celsius and we have data at 30 degrees Celsius. If you see, The curve that we have on our TV plot can be well approximated by a straight line between those two data points. 20 and 30 degrees are close enough on that line that if we do a linear interpolation, meaning we assume that a straight line connects them, that should give us a very good estimate of the value of the specific volume at 23 degrees C. So let me get rid of that box because it's distracting, and we'll do work over here on the right. The assumption of linear interpolation is that the slope of that line is constant over the entire region of interest. The slope in this case is just delta t divided by delta v, so we're assuming that's constant, but we could write it in two different ways. We could say that the slope between the 20 degree point and the 30 degree point is some value, but that should equal the slope between the 23 degree point and, for instance, the 20 degree point, because we just said the assumption is the slopes are constant. So if we write that out, on the left-hand side, we have the slope between 30 degrees and 20 degrees. It's just 30 minus 20 divided by the specific volume at 30 minus the specific volume at 20. If the two slopes are equal, that should equal 23 degrees minus 20 degrees divided by now the specific volume at 23 degrees minus the specific volume at 20. Well, we can rearrange for this. Ultimately, remember, we want to solve for the specific volume at 23 degrees, so we want to solve for v sub 2, 3. So let's move that over to one side. That temperature ratio on the right-hand side is just going to turn out to be 3/10. That'll be unitless because it's a ratio of temperatures. And now we can add V20 to both sides so that we solve for V sub 2, 3. So we do that, and we see that V23 equals V20 plus 3/10 times the quantity, V30 minus V20. Now the nice thing is, we did all that work looking up these states. We know the values of V20 and V30, so we know everything on the right-hand side. Let's plug in those numbers. So we do that here, go through and do a little bit of math to simplify things, and we see that our estimate for V23 is 0.09518 cubic meters per kilogram. Now, an important sanity check to do after any linear interpolation is that the value of V23 had better be between the values of V20 and V30. That's the whole idea behind an interpolation. So we check, and indeed, our result is between V20 and V30 as required. If we had found an answer that was bigger than V30 or smaller than V20, we would have known we had done something wrong. Either we had miscopied a number, looked in the wrong table, or potentially just performed a math error as we were doing this calculation. But as we can see, our result is very nicely bounded between the two, and it's even a little bit closer to V20 than to V30, as you might expect, since we're dealing with 23 degrees, which is closer to 20 than to 30. Everything checks out, it makes sense. This seems like it should be a very reliable estimate for the specific volume at 23 degrees Celsius and 2.4 bar for refrigerant 134A.